Hello and welcome to this video on reactions of alkenes. And what we're going to do in this video is two things. First thing is we're going to have a look at electrophilic addition reactions. Electrophilic addition reactions. Specifically with hydrogen bromide. And you'll be familiar with addition reactions and electrophilic addition reactions. Just take it one step further in terms of detail. So that's be the first thing that we'll do in the video. The second thing is that we're going to have a look at asymmetrical alkenes. So if you look at this alkene on the right hand side here, you could draw a mirror line down the middle and it would be symmetrical. What's on the left is the same as what's on the right, but that's not true of most alkenes. In fact, let's draw an asymmetrical alkene. Right, so you could have a double bond there and a carbon with a methyl group, one hydrogen, two hydrogens here. Let's just put the hydrogens in for completeness, and you can see if you draw the mirror line down the through the double bond, what's on the left is not the same as what's on the right. So if you were to react this with hydrogen bromide, the bromine could go onto that carbon when the double bond is broken, in which case you get one molecule, or the bromine could attack this carbon and go on that carbon instead, in which case you would get a different halogen alkane. And so we're going to study that in some more detail and decide which one happens most often. That's what we're going to do. Yes, so let's start with electrophilic addition reactions of alkenes with hydrogen bromide. Picking a specific reaction, let's work with ethene. So we've got, let's do the molecular formula first. Ethene, C2H4. We're going to react that with hydrogen bromide, and we're going to get the halogen alkane bromoethane, like so. Now, if we're doing the reaction mechanism, we need to draw out the displayed formulas. So here's ethene. Like so. I'm going to draw a hydrogen bromide down here. Right, and as you know, hydrogen bromide is a polar molecule, so our hydrogen is going to be delta positive and our bromine is going to be delta minus, because bromine is very electronegative. And we've also got a very negative area in the double bond as well. So those electrons in the double bond, they are going to attack the delta positive hydrogen, like so. And when they do so, the hydrogen bromide bond in hydrogen bromide breaks and the electrons stay with bromine, and we draw that curly arrow to illustrate that, like so. So once those two things have happened, then we get an intermediary. We're going to draw out the intermediary first. We've got our carbon. Still got two hydrogens attached to it, like so. But our double bond has gone. This hydrogen will come back to. We've got the two other hydrogens still, like so. But this carbon is positively charged now. It's called a carbocation. And so let's just track some electrons before we go any further. Let's switch to red, and we can illustrate these two electrons in red here. They're the ones, this is the double bond that was broken, and so they become these two electrons here, bonding to the hydrogen that left without its electron. Right, let's switch to, say, green, and do these two electrons here. And they both went to the bromine, and so the bromine here took both of those electrons, so that makes the number of electrons it's got up to 8, so it has a negative charge, and those two electrons we can draw as a lone pair, like so. And just for completeness, let's draw in light blue. Let's choose purple and overwrite this hydrogen here. Let's put a circle around it as well and illustrate that that's the hydrogen there, the new hydrogen that's bonded to that first carbon. Okay, so now we can go back to the reaction mechanism, and we can see that we've got a positive carbocation and we've got a negative bromide ion. They're going to attract each other, so the lone pair on the bromide ion is going to attract that. It's going to attack that carbocation, so we draw a curly arrow like so, in which case we get our completed bromoethane molecule, which we draw like this. Where this is our bromine, this is our hydrogen, like so. And we can do our electrons again. Let's go to red. Let's go to green, and the two electrons in green become these two electrons, and we've already done the other two electrons. The positive charge on the carbocation and the negative charge on the bromide cancel each other out, so the end product is neutral, as you'd expect. And there we have it. That is the electrophilic addition reaction that we dealt with before, but it's good to have a reminder because now we're going to go and look at this reaction mechanism as it happens in asymmetrical alkenes. And the addition of hydrogen halides to unsymmetrical alkenes leads us on to this concept of the stability of a carbocation. So that is an alternative title that we could have. You could call this little concept here the stability of carbocations. Right, you'll see why in a second. Let's go back to the example that we had on the very first slide, where we had propene, didn't we? Let's draw out propene again, like so. For time I won't draw in the hydrogens, right, and we're going to react that with hydrogen bromide, and as we saw, we could have got two products, couldn't we? The bromine could attack carbon number 1. If this is carbon number 1, that's 2, and that's 3. So you could, if the bromine attaches to carbon number 1, you get this molecule. Which is 1 bromo propane, 1 bromo propane. Equally, the bromine could attach to carbon number 2, in which case you would get 2 bromo propane, like so. And the carbocation that was created as the intermediary in each case is going to be different. Carbocations are generally classified as primary, secondary, or tertiary. If we look at our top reaction here, this one here, and I draw carbon number 1 first, that would be the carbon atom that has the positive charge, and you'd have 2 hydrogens on it, which are these 2 hydrogens here. And then if we just, for generic purposes, call this an alkyl group, which we can call R, you can see that we've got 1 alkyl group and 2 hydrogens, right? And so that would be called a primary carbocation, which can be summarized with 1 degree like that. Whereas if we now study the second reaction, the carbocation intermediary that would have been produced in that reaction would be like this. This in green carbon here is this green carbon here. So that would be the carbon that would have the positive charge on it, and it's still got a hydrogen, which is this hydrogen here, right? But it's got this alkyl group on it here. Let's call that R1, and it's got this alkyl group on it here. Let's call that R2, like so. And now you can see that it's got two alkyl groups. The carbocation has got two alkyl groups attached to the positive carbon and one hydrogen. And so this would be called a secondary carbocation, which is summarized like that, 2 degrees. And you also get tertiary carbocation. So let me draw you a tertiary carbocation. Let's pick purple, seeing as it's different. So our carbon that has the positive charge on it would then, as you I'm sure are guessing, would have 3 alkyl groups attached to it, like so, and that would be called a tertiary carbocation. Let's draw it in words as well. TER, tertiary carbocation. Now, what we said at the top here, the stability of carbocations, is really what this slide is all about, because that determines how much of the end products you get. Okay, so the stability, the trend of stability is that the tertiary carbocation is the most stable. The tertiary carbocation is the most stable, and the primary carbocation is the least stable. And that is because in a tertiary carbocation, the positive charge that's on the carbon atom can be neutralized to a certain extent by the electron clouds that can come from the alkyl groups. So the electron clouds that are around the atoms in the alkyl groups can spend a little bit more of their time nearer the carbon with the positive charge, and that sort of spreads the positive charge out a little bit, makes it less dense, and that makes it more stable. And if, let's draw a little important statement in this box at the bottom down here, if a carbocation is more stable, it is more likely to be formed. All right, so stable carbocations are more likely to form, and therefore when it comes to making products, you know, it's not in the example that we did before with 1 and 2 bromopropane, it's not a 50-50 chance. All right, if the carbocation in making 2 bromopropane is more stable, because it's a secondary carbocation, and therefore is more likely to form than the primary carbocation, then more often it will form, and therefore you will get more of 2 bromopropane than 1 bromopropane. It's not a 50-50 chance. There, hopefully that's clear. Watch the slide again if it's not, and if it's still not clear, ask me. So let's finish off by having a look at a real example and do the reaction mechanisms for, in this case, both halogen alkanes that can be formed. Starting off with naming this product, you can see we've got 2 methyl groups attached to carbon number 2. This is carbon number 2. So we're going to have 2 methyl, and we've got 4 carbons in a chain. You could call that carbon number 1 if you want, carbon 2, this would be carbon 3, and that would be carbon 4, in which case it's bute, and our double bond starts on carbon number 2. Right, so the name of this is going to be 2 methyl, 2 methyl bute, and it's going to be 2-ene that's how we write it like that. And then we're going to react that with hydrogen bromide as usual. Okay, so here's our hydrogen bromide, and as you know, our hydrogen is delta positive and our bromine is delta negative. So that's the starting point. Now, our double bond is highly negative. It's an area of high negative charge density, and that is going to attack our delta positive hydrogen atom. Now, if in red we do these two electrons here, those two electrons could form, could stick with carbon number 2, in which case, you know, you're going to get a double bond down here, and we can call that reaction mechanism 1. So if we do that, you're going to get your carbocation that looks like this. Okay, so there's our carbon number 1 with our 3 hydrogens. There's a carbon number 2. It's got its other methyl group, the second methyl group there, and this is hydrogen from the hydrogen bromide, and then this would be the carbon that has lost its electron because it's just gone here, and the rest of that carbon, that is the same as it was before. Now we can draw it out like that, and for completeness let's put our hydrogens on. Right, so that's our intermediary, and when that happened, let's remember that both these electrons that were in the hydrogen bromide left to go on to the bromine, what becomes a bromine ion, and so we can go and draw our bromine ion here. So we're going to draw it like this. It's got a negative charge because it's picked up that extra electron that was hydrogen's electron, and so we're going to let's do these particular electrons in green because they were those 2 electrons there, and they fancy the carbocation there, and so they are going to attack it. So we draw a curly arrow pointing towards the positive carbon, and that's going to give us the final halogen alkane, which we're going to draw like this, and we can now draw our 90-degree bond angles. That's our 1 methyl group, that's our other methyl group, and notice I've done the CH3 reversed because the bond has to go to the carbon. That's our hydrogen that was with hydrogen bromide. That was the carbon that did have the positive charge but is now bonded to bromine, and the rest of the molecule looks like this. Okay, we can name this now. So in our longest part of the chain, we've got 4 carbon atoms. So the name is going to finish with butane, but we've got 2 groups attached to it. We've got a bromo group and a methyl group. B of bromo comes before M of methyl. This is our methyl group here, and we want the lowest number. So bromo is going to come first in the name, and because B becomes before M, we want the B to be on the lowest number of carbon. So we're actually going to number the carbons from right to left. So this is number 1, that's number 2, that's number 3, and that's number 4. Okay, so our name is going to be 2-bromo, right? Because the bromo is on carbon number 2. Let's start it over here, 2-bromo. Now our methyl group is on carbon number 3, so it's going to be 3-methyl. 2-bromo 3-methyl butane is the name of that product. Okay, so that's one of our halogenoalkanes. Let's do the other one. Recapping what's happened. Hydrogen bromide has come close to our alkene molecule here, our 2-methyl butene, and the negative charge of the double bond has fancied a bit of the positive charge of the hydrogen in the hydrogen bromide, and it's attacked. But this time, let's overwrite the two red electrons with purple electrons, because they are going to instead stay with this carbon and form a new hydrogen there. In which case, we get a carbocation that looks like this. So this is carbon number 2. It's still attached to two methyl groups, like so. That double bond is broken, and those two electrons, the purple electrons there that we drew in, have bonded to our hydrogen, leaving this one positive, and the rest of the molecule is the same, like so. And again, we've got a bromide ion with those two green electrons. We can draw those in green, I suppose. We can draw those two green electrons, and they fancy the positive charge on the carbon, so they're going to attack that, in which case the product looks like this. And the bromine goes where the positive charge was. That was a hydrogen that was in hydrogen bromide, and the rest of the molecule is the same. Okay, and as you can see, we've got a different molecule. Actually, it's the same product upside down, isn't it? Let's just name it to show us that. So we'll number our carbons again. So this time we're going to number from the left to the right. 1, 2, 3, 4, because we want our B to have a lower number on it. Okay, so now because we number to the left, it's still 2 bromo, and our methyl group is on carbon number 3. No, it's not. Our methyl group, this is our methyl group here, is also on carbon number 2. So it's 2 bromo, 2 methyl butane. So it is a different molecule. Okay, so they're the two molecules that we're going to make. Let's review which one you would get more of. And if you remember from the previous slide, you get more of the halogenalkane that arises from the more stable carbocation. So let's have a look at our purple carbocation first. And is it primary, secondary, or tertiary? Well, here, this is our carbon with the positive charge on it, and you can see you've got one methyl group that I'm arrowing there, another methyl group that I'm arrowing there, and a third methyl group here. So this is a tertiary carbocation. Okay, so that's going to be pretty stable, in which case it gets formed a lot, and if it gets formed a lot, the bromine will have more opportunity to attack it, in which case you get a lot of the 2-bromo 2-methyl butane. Okay, let's look at our red carbocation at the top there, and this was our carbon with the positive charge, but this is a hydrogen. This is an alkyl group, and this is an alkyl group. So this is a secondary carbocation. So whilst more stable than a primary carbocation, not as stable as a tertiary carbocation, so you will get less of the 2-bromo 3-methyl butane. There we have it. That's the lesson finished. Hopefully that's been clear for you.